Okay, so I think we can start now. Good morning to everyone. I think Professor Schmidt already introduced me last week. My name is Stefania Tapias. I'm a PhD student at the Chair of Information Architecture, and I'm going to give you today's lecture. We're going to talk today about climate, and in particular about urban climate. So it's thinking. Everyone is here, right? Okay, so today's lecture, it's divided into 6 parts. At the beginning, I'm going to introduce you about the definition of what is urban climate. Also, I'm going to talk about a little bit about urban energy exchange in order to understand a little bit more about the consequences of urban climate. Then I'm going to give you a context about why it is important to study the climate in the city. I'm also going to introduce you about outdoor thermal comfort, then about bioclimatic design, that I'm sure most of the architects know a little bit about it. And then at the end, I'm going to show you some tools to be able to measure the climate in the city. So by the end, I hope you will understand about the urban climate and its importance to urban planning. Also, identify the different scales and layers in the city for the urban climate. Also, recognize some strategies that are developed in the city to enhance the comfort and the climate in the city. And then also at the end, identify some tools. The idea is not that you completely understand them, but that you have an overview of what it's out there to be able to measure and to analyze the different parameters in the city about climate. So what is urban climate? Before we have to understand what's climate. So climate is a pattern of variations of different measures of weather that occur in a given region for a long time. So it can be temperature, precipitation, humidity, sunshine, wind velocity, etc. Then the urban climate refers to these particular conditions, but that occur on the urban area, on a city, on a town, or a configuration of buildings. And it's mainly attributed to especially the urban development. So we have 2 different layers where we study the different type of climates in a city. We have the urban boundary layer, which is actually the one it's the layer that goes from the rooftops of the buildings up. And then we have the urban canopy layer, that it's the other one that goes from the rooftops down, which is in particular the urban canyons or the street canyons. The urban canopy layer, it's denominated by its nature of the immediate surroundings, so the buildings, the materials, the vegetation, the trees, all of these immediate surroundings. And then also, apart from the layers, we also have the different scales of urban climate in a city. So we have the mesoscale, which is the urban region, or the urban scale, the region scale, sorry. Then we have the local scale, which is like a single urban terrain zone or land use. It can also be a neighborhood. And then we have the micro scale, which is in particular the street canyons. So are you familiar with the term street canyons? Is there someone that it's not? So the street canyons are, in very simple words, is the atmosphere between 2 buildings. So it's all is there a pointer here? No. It's mainly this part. So the air between, or the environment between 2 buildings, that you can also find it in the streets. And then we have in the microscale, it's where we study the microclimate. So the microclimate, it's defined by the climate that prevails in this microscale level of the city. And this is where we're going to focus today. So why all of this is important? So as most of you know, the urban population growth is increasing. And then since 2010, and others say that since 2012, but around this time, more than half of the people live in cities, and this number is expected to grow around 1.5% per year. And the other very important issue is that this growth is going to occur mainly in developing cities. And also, why is this important? We are facing the changing or the climate change phenomena right now, and cities are seen not only as the main contributors of this change in climate, but also as the potential sites of climate vulnerability. So every time the climate starts changing, the cities are the first that have the biggest disasters. And as a consequence, or one of the phenomena that we see from the climate change is the urban heat island. I don't know if someone has heard of it before. Has someone else? I'm sure someone has heard of it. Yeah? Okay, good. So the urban heat island, it's mainly the increase of temperature in the city. It's in simple words. And then different causes of this urban heat island. One of them is the anthropogenic heat, which is the heat emitted or from human-made activities, so vehicles, industries, and in this case, air conditioners. This is a picture of Singapore taken by Marcel Brulisauer in the FCL, in the Future Cities Laboratory, and he was studying in particular the effect of the changing in temperature in the city based on the air conditioners. So how it will be more strategic to place these air conditioners not in the facades, but in the rooftops. And then another cause is the configuration of buildings in terms of the solar radiation absorbed in the cities because of the materials of the buildings, because there's more lack of green areas, lack of trees, lack of vegetation. And also this configuration is also affecting the different ways in which the wind can enter a city and in which can flow. So this can also affect the urban heat island. So also, as we saw before, we have the different layers for studying the urban climate. We also have different layers of urban heat island. So we have the boundary layer heat island, which is in the boundary layer, as we saw it before. We also have the canopy layer heat island, and at the end we also have the surface heat island, which is mainly about the surface, about the materials and the floor and all of this based on the materials and the elements. The first two are studied or are seen as urban heat islands in the air, like it's more the air, and then the other one is more about the surface. So to understand a little bit more about this change in the climate, in the microclimate, we have to study the surface energy balance, or how the energy exchange works. So the urban energy balance is based on the first law of thermodynamics that says that energy cannot be created or destroyed, but it's just changed from one form to another. So it's actually the same theory behind it. So the energy balance can also be the change in internal energy equal to heat added to a system minus the work done by the system, in simpler words. The difference between the total incoming and the total outgoing energy of a physical system. So if the balance is negative, it's cooling occurs. If the balance is positive, warming occurs. So I hope it was easier. So the energy input is equal to the energy output plus the change in storage energy. So it's just a system that changes the energy according, if it's positive, it goes warmer, if it's negative, it goes cooler. So I hope it's simple. And then also to understand a little bit more about this energy exchange, we have to know in which scale are we. So again, we see the different layers. And then we see that the surface energy balance occurs in the mesoscale. So as I don't know if you remember the slides before, but this is one of the scales of the climate, of the urban climate. So the energy transfers mainly in this part, and there's also an equation that says that the main two causes are the net radiation and the anthropogenic heat, and then the different exchanges are different flux of energy, of heat, sorry. So, is there any question until now? No? Okay, so now we're going to see the autothermal comfort, which works similar to the energy exchange, because the autothermal, it's also the exchange of energy, but the thermal exchange between the human and the environment and the air. So why is this important? Because the outer spaces in cities is important to maintain the people comfort. So these spaces can be livable and can be successful. So it's very important to study them and to understand the comfort of the people and to be able to manipulate the environment to enhance this comfort in the different open spaces. And then there are different ways of measuring this autothermal comfort. So it's not only about qualitative measures, but also quantitative. There are different ways, different thermal index to measure these ones. For example, the one I'm showing right now, it's the physiological equivalent temperature, which is a measure that combines the local microclimate conditions and the human thermal sensation. So, for example, what it mainly tries to link is that in cities or in countries that are very, very warm, people are used to have warm conditions. So for them, a warm weather can be 29, rather than people living, for example, in Europe, that it can be very cold. For them, warm it's 23 degrees Celsius. So it's kind of the relationship between a more human perspective of the sensation of climate in the outdoor, according to the cultural and to the different locations around the world. So also because of this, we need to have different requirements for different places in the world. So the requirements in Singapore are completely different from the requirements here in Zurich and so on. And then the design means are based on this requirement. So from here, we start looking at what is bioclimatic design. So bioclimatic design is the design that takes into account the microclimate conditions of the surroundings to lower down the energy consumption and to use more energy sources of passive heat and cooling. So the approach of architecture, so in bioclimatic design, we have into account the site and the climate analysis, the heat energy exchange, as we saw it before, and some design strategies to reduce this energy consumption in buildings. The principal criteria you have into consideration when you're designing a bioclimatic building are, for example, the sunlight, so in terms of isolation, shading, and orientation, and the wind in terms of airflow. And then this can give different thermal conditions and in terms of temperature, and can affect the heat energy exchange. So, but today we are more, we want to look more into the urban scale, so the approach for urban design. So we have different examples of how we can iterate or how we can manipulate the urban surrounding to manipulate the urban climate. One of the examples could be the wind breaks. So you can actually configure the buildings in different ways in which you can enhance the circulation, the airflow circulation, according to the prevalent winds of this particular place. Or on the other side, you can use the sun shading, so you can make different calculations of how the shading analysis is. Or, for example, in the picture I have here, this is a simulation of the shadow range analysis during a period of time in a particular place. So taking this into consideration, you can make design decisions. So the goals in the urban design or bioclimatic urban design, first are to change the configuration of building for the reducing energy consumption. So in this case, it's more how to build or how to design a configuration of buildings in the way that you don't obstruct or that you enhance the solar rights into the neighboring buildings, and that you can change and how you can affect the neighboring buildings in particular. And then the other one is the configuration of urban spaces to enhance the orthothermal comfort. So as I was saying before, when we were talking about orthothermal comfort, you can change the different configurations of buildings or of urban forms around public open spaces and actually enhance the comfort, the thermal comfort. So this is an example that it's called the solar envelope concept, which was introduced by Ralph Knowles, and it was a strategy to provide solar access needs according to building geometries. So he actually did it everything by hand. He studied the whole solar path of a particular place, and then he did some geometrical analysis, and he created these forms of buildings or these building envelopes in order to not disrupt the neighboring buildings and to take the most of the solar rights. So this is one of his examples. So he made this building envelope, for example, here, and then he started designing the buildings from inside this building envelope. So they look the same, more or less. They have the same angles, and it's the same envelope, and then he just started developing even further inside.
Where is this exactly? Is it like in Europe or in?
No, this is in the US.
US,
in particular.
so it's capturing sun is profitable.
Yes,
okay.
yes. Yeah, that's a good point. It really depends where you do the design or where you make this analysis. In the US or maybe in Europe, it's good to have more sun. But then if you do some in, I don't know, Africa or Latin America, then you have to think a little bit more about, okay, we don't want sun, we want more shading. So the strategies change. Also with the wind, they also change. Yeah, this is another example. It was more like a neighborhood scale area he did. He made the different envelopes, and then he developed the different houses inside. So you have to know that this was not, this was quite long ago, so he didn't have any computational help to do this, but right now we do have that. That's what I'm going to show you later. And then talking more into wind. So you have to know that wind, it's a little bit more complicated to simulate or maybe to predict, because wind has a very difficult way of reacting after it arrives to the different obstacles. So it's not like sun. You always know that the sun has the same path, and then you always know that the shadows create in the same way according to different locations. But the wind actually changes quite a lot, not only because of the locations, but also because of the different elements the wind can arrive to, so the different obstacles. So we have also different scales of how to study the wind. Today we're only going to look only into the first two, which are the ones placed in the microclimate scale. And then we have first the wind near the ground. So we always know that the wind flows horizontally. And that when it arrives to an obstacle, the wind changes. So the flow of the wind and the patterns change. This is things that we already know from history and from what we've studied wind from before. Also, we know that according to the windward, which is the facet where the wind starts or when the wind arrives, the wind reacts different. So according to how the geometry is in the facade, the wind always reacts different. And then more into the urban canopy layer, the wind directions extremely vary. Also because of the canyons, so they create different patterns after they arrive to the obstacle. So that's quite complicated to study, but we have some ideas of how it can react. So also we have some ideas of how we can design according to the wind. So for example, in this image, we can see that if we have different buildings in different heights, we have more ventilations through the canyons. And so now I'm going to show you some tools that have been there for quite a while to measure and to have an idea of how the wind in different locations are. So for example here, this is the wind rose. I'm sure someone has heard of it before. So do you know more or less how it works? Does someone knows how it works? Does someone wants to say how it works?
Well, you can see, for instance, in the northeast that there is 4% of the time plus 23 knots per year.
Yep. Yeah. So yeah, that's true. So it shows the direction, the prevalent direction of the wind, and the speed of the wind at the same time. And so normally in every location around the world there's a different wind rose, and it's not that complicated to find it. You can find it in the internet. Each country has its own different wind rose for each locations. And then we also, for the sun, we also have a similar or quite different tool. It's called the stereographic sun path diagram. It shows in a 2D the sun path during the year and then during the day. So the different days of the year and during the whole day, different hours of the day. And then you can actually also overlap that with shading requirements. And then we also have another one to measure some parameters. We have the solar insolation, which is the amount of solar radiation reached into a surface. In climatology and urban climatology, we also use quite a lot this measure. So now I'm going to show you some tools that we have until now that it can help us to measure and to simulate these different climates. So in terms of softwares, we have general measures for all of these parameters. So the first I'm going to show is the different we have for indoors. So we have energy analysis, thermal performance, water usage, daylight, wind, solar radiation, and shadow range. But for urban planning or for the urban scale, we actually only use the last ones because we don't want to. We don't have any water usage for the urban scale. We actually just use the last ones. And then we also have different other tools, but this is another story. And then in terms of software, we have one that it's maybe kind of the oldest one in terms of architectural design, because of course, if we go more into engineer, there are a lot of other tools that engineers usually used. But for architects, this was actually the first tool that really visualized the measures. So it's called Autodesk Ecotech. I think they're going to end it also at some point because they're going to replace it with another software. But this was quite an easy to use tool and it was really nice for architects because it could really visualize the different data and the different measures for this analysis. Also, into more parametric design, we have the DIVA for rhinoceros. I don't know if you've heard of this one. This is more an analysis more for solar rights, so everything that has to do with the energy performance inside buildings and also the solar rights that arrive to a building. Have you heard of it before? Okay. And then we also have, so this is actually the roadmap of these tools that I've shown you before. So you have the model, you have the analysis, then the analysis gives you some data, but then you had to go back to the model and redo the analysis. Because this was not the most efficient way of doing this analysis or the simulations, the other tools, parametric design tools, arrived. And the idea of this is to minimize the effort needed to create the test design variants. So you can actually just model, then analyze, then change, then iterate, then model, analyze, change, iterate, and then it can be parametric. So for this we have different tools. So one of them that it's quite new for the wind analysis mainly, it's called Autodesk Revit Vasari. I don't know, has someone heard of it before? Okay, good. The problem with this CFD tools, these computational fluid dynamic tools for the wind, is that the technology is not there yet that really simulates how wind flows and how wind reacts after it arrives to the obstacle. So this is a good tool to have an idea of how the wind can flow, but it's not a very reliable one because it's not really precise. That's the problem with this kind of simulations. But for architecture and for the pre-design period, it's good to have. It's not a bad idea to use it. It's good to have like first insights, but it's not very reliable when you want to go deeper into the simulation. Then we have even more parametric modeling and visual programming tools. We have Grasshopper in one side and then Dynamo in the other one. In the course that I do with another of our colleagues, I don't know if some of you are in that course, maybe one or two. We're actually using the Rhino Grasshopper to do this type of simulations and combine the simulations in a parametric design workflow, but we also have the other examples like Dynamo that this works pretty much the same. And then for environmental analysis, we can also connect these parametric design tools or these visual programming tools with the tools we saw at the beginning and with different analysis on shading or on solar insolation or on wind, and we can connect them, and it's easy to use also because you can run the simulation, then change, and then run it again, and then change, and then run it again. So it's actually a good way for design and planning. Then we also have, inside this visual programming, we also have different tools or small tools. And I wanted to show this one because this one is actually based on the urban envelope, solar urban envelope that I showed you before. So these guys, what they did is that they took the theory out of the solar envelope and then they created a component in Grasshopper to recreate the solar envelope. So you can actually have it also in digital, and you can work with it inside a modeling software. And then this is just some idea or some tools that we've been developed that are more, for example, this tool is more about the shading. So this is showing a simulation of the shading during the year, and then during the year and during the whole day. And then in this tool you can then add different geometries or different buildings you wanted to add, I don't know, in an urban location, and then you run again the simulation, you run again the simulation of the shadow range analysis, and because it's based on a parametric design tool, you can also change the different parameters of the geometry, and you can see in real time how the shading changes. So this is a good way of using these tools. And also you can also go even further and use different algorithms or, for example, evolutionary design methods. In this case, I think I didn't started it. Yeah, I think the video doesn't work, but it's here we used evolutionary design algorithms, and in this particular was the genetic algorithm, and it was used to find the perfect or the more accurate, adequate point in this urban block that can meet different criteria of shading. So we had the winter shading and the summer shading, and then the idea was to, according to predefined criteria, to find the optimum place in this urban space. So, to conclude, just some general remarks. So, urban climate refers to the climatic conditions in an urban area and that differs from its surrounding. Also, urban microclimate, it's defined as the climate that prevails in a microscale level. I hope you have that clear. Also, that the anthropogenic heat is one of the main causes affecting the microclimate conditions. I don't know if you remember what anthropogenic heat is, but it's the heat emitted by human-made elements or activities. Then studying the effect of the urban microclimate, it's important to overcome contemporary issues of cities, so creation of urban strategies according to the climate. So it's important to understand, because normally and some new designs of architecture, they talk a lot about bioclimatic design and climate sensitive design, and they try to just adapt some things to the regulations. But the problem here is that most of these activities, they don't understand what is really the climate and what's really the urban climate and what it's really affecting this climate. So it's really important to know and to understand what it is exactly. And also, I hope you also had an overview of the different tools that you could use eventually if you want to continue in this field, or if you are more interested on how to design with the climate. So I hope you had a big overview, and in case you want to know a little bit more about it, these are 4 books that I chose that I think can be a good way of starting with this topic. Actually, the first one, the Urban Microclimate, it's really about how to design according to the climate. So it's actually a very good book. And then some references if you want to know a little bit more about it. I think we can share this presentation. Yeah, okay. So are there any questions? Yes?
In cities, since there are more and more built objects that absorb heat and less greens and parks and stuff, is that more an anthropogenic or configuration of building factor?
I didn't get the first part, sorry?
For me, I always imagined that the most important factor of cities being warmer than outside was because it was only built fabric and roads and buildings and no more trees and parks.
Yeah, that's more about the configuration of buildings, which is linked to the absorption of the solar radiation. Okay. And also, yeah, it's mainly that. But it can also be the anthropogenic heat, because if you talk about streets, you also have to talk about the vehicles. And then also if you talk about buildings, you also talk about the industries that emit CO2 and all of these things. So it's actually very, very linked. Okay, good. Another question? No? Are you happy? So, yeah, I don't know how many of you are architects right now. Are you a lot of architects here? Yeah, okay, good. That's a good amount. So I hope you had an idea of how important it is to understand the climate for the design. Good. So I think we're finished.
Yeah, thank you very much for the last lecture of today.